Welcome to Put a Type on It. Together, we're going to go on a journey about discovery. And this is, in part, now that I've got you in this room, this is my confession, right? This is about Idris type providers, but it's about my philosophy on how we can make infrastructure and software a lot more reasonable. So I'll be your host. My name is Susan Potter, and for the last 10-ish years of my 18-year career, I've been trying to build services that are a bit more reasonable to varying degrees, right? And I've done a lot of work with distributed systems and back-end kind of stuff, but a lot of people actually know me as a Ruby developer. And I also have done my fair share of slinging Java, and apparently some people think I should be endorsed for agile methodologies. I hope they were jokes, but I share this because my experience is very. How many of you are in industry? You're not researchers, right? Yeah, the vast majority of you. And how many of you work on what many would consider mainstream stacks? Okay, great. So that's most of you. That's great. That's kind of what I've targeted this talk at. And so if I can do it, there's hope for every single one of you people, okay? And not that I've done anything, right? But I'm sharing my experiences with you, right? Okay, so questions, feel free to ask questions. They're welcome throughout the session. I will be checking in with you, right, as well, right? But do feel free, if there's something on the slide that just doesn't make sense, or you think it's a typo, please bring it up. I might defer some of the more philosophical questions to the end. Okay, so I was going to put in a PHP error in here that I got one morning this week, just randomly on the web, right? As an example of a type error, and that was really a lame straw man. So what I'm going to do here is I'm going to show you an error that I think most people would not consider a type error, or should not be a type error, or I don't know that they would think it would be a type error. And that is, how many here are familiar with AWS EC2 kind of lingo? Okay, most of you. Well, EC2 is part of AWS, Amazon Web Services, and you can launch instances which are kind of like virtual servers, right? And so I'm just trying to explain some of the terminology. And if you launch an instance, and one day I launched an instance, and it gave me back this, right? And so basically what this is saying is that my account did not actually have the ability to spin up an instance in this availability zone. Now this is actually from a few years ago, before VPCs, but it still kind of counts, right, I think. And basically availability zone mappings are specific to the account, and they're per region. So AWS has this notion of regions. If you wanted to put your server infrastructure on the east coast of US, there's US East 1, right? And if you wanted to kind of target maybe West Coast users, there's US West 1 and US West 2, right? And this is actually what my mappings look like on my account, right? This is actually this is my personal one, right? This is like one of those started out as a free tier thing, and I hardly use it, right? But I've got 2 availability zones available in US West 1, 3 in US West 2, and 4 in US East 1. Now this happened, like I only had 3 availability zones just a couple of months ago, and so this grew in the last couple of months, and I didn't know about it. I don't know where you find out about this kind of stuff, but Amazon just adds them, I guess. I don't know, right? So this is a common solution. So I've worked with a lot of Ruby, right, on infrastructure and server code, right? This is kind of very typical. Now, it may not be hard-coded per se, right? It may be read in from a YAML file or something like that. But typically, there's some kind of thing where people manage, the bindings or the mappings of the availability zones per region, right? And they'll do something like this. And, well, what's the problem with this, right? Well, Well, the problem with this is, well, whether you're hard coding this in Ruby or you've got 2,000 lines of config YAML files, right? By the way, that was a quote from this afternoon. I heard someone just randomly say that. So this exists, by the way. And to be honest, I think I've seen 1,000-line config YAML files, right? So over time, this kind of thing leads to stale assumptions about your operating environment, right? It is also kind of a very reactive thing. You usually don't always, I mean, your organization usually doesn't have someone who is committed to updating those files, right? As soon as you get availability zones available, right, to your account, right? You also have, typically, a lot of organizations have multiple accounts, and those mappings are totally, dependent on the account. So this isn't code that is transferable across many accounts. So what can we do about it? Well, okay, let's talk a little bit about the problem space that I'm really looking to solve, right? Number one is that I want to have these derived rules and policies, right? So I want to have this generic idea or template of a rule that I want to apply. This could be a rule that's related to some consistency or availability concerns on the infrastructure side. It could be something related to finance, right? So one particular service can't use more than so much a month, right? Or shouldn't, or it should alert, or something along those lines. Or it could be just simply that the service engineers say, oh, well, this system needs to have, needs to be deployed or provisioned with EBS optimized machines or something like that. Now, those are the kinds of policies that I actually do want to be able to define, right? I want to define that in a highish level language, right? And I want it to be something that we can evolve over time, and that is fairly simple, right? I also want to be able to validate existing deployments that are already in the our cloud, right, providers. And I want to get to the point, too, where we can validate deployments against policies before we even deploy in the first place, right? And over the long run, I want this high-level language that is that can give us some assertions, right? It's not just managed. It's not just an imperatively defined sort of bit of Ruby code that does this. Because what we could have done is we could have had Ruby hit the service that tells us what availability zones are available to our account, right? But then we have like all of this, code dribbled all over the place, right? And it's not necessarily the kind of thing that I want to be managing, right? And it also doesn't give us very many assertions or assurance of that our validations are in fact sound, right? And we'll get to that towards the end of the talk. So why reason about infrastructure now? I think we're at a point where distributed systems, you can't get away from them, right? So we have to deal with this complexity anyway, regardless, right? We have this always-on kind of need, so we need to deal with it. We also have really high churn and turnover in operations especially, but also developers. And this creates a work environment that I think is demotivating. It is exhausting. It is tiring, and it doesn't produce the best kind of the most creative or innovative solutions to a problem, right? And it just burns people out. This is not the kind of environment that I want to work in. And I think a lot of people are starting to realize this and starting to acknowledge this as a problem. And technologically, I think functional programming and expressive type systems are no longer for academics. And I think especially on the functional programming side, there have been lots of inroads made all over the place from front end to back end. And also now I think we're starting to see some being done on infrastructure side, right? And expressive type systems, sure, there could be a little bit more work done to make that more accessible to industry developers, but it's getting there, right? And I'm definitely seeing strides in that direction. We also have programmable infrastructure everywhere, right? So whether you've got a data center, you've probably got something that you can program against. Whether you're in AWS, Google Cloud, it doesn't matter, right? So these kinds of things are realities now, and I think this is hopefully going to create a turning point for us, all these three things kind of converging at once. Okay, so what is a type provider? A type provider, it's a mechanism for constructing types, right, from external sources. So if you wanted to, you could create types for your database schema, right? You could create types based off of JSON data. You could create types based off of the header information of a CSV file. These kinds of things. And so the schema, or the metadata, needs to be somewhat stable for the duration of the running program. And the running program is the compiler, right? The type checker in this particular case, right? And of course, you want to be generating programs that'll be valid for a little time, right? But our requirement is that at the time of deployment and provisioning, we are able to take advantage of all the capabilities that our AWS account gives us, right? And that's not just availability zones per region. That's also the kinds of services that are available to us in different regions, right? So some accounts are kind of preferred accounts, and they get early access to certain things that are only available in certain regions, right? And some service developers may want to be able to deploy there. Okay, so how do we make, so how do type providers work? Well, a lot of them in other languages like F# and Scala and Haskell, although not necessarily all of them, utilize some form of source or bytecode generation as part of the solution. And so that's how they build their types. And that's cool, but it also doesn't mean that we can reason about whether or not the program that they've generated behind the scenes is actually well formed. Okay, so this is what a JSON type provider looks like in F#. And on line 6, the interesting thing here is that we give it a prototypal kind of bit of JSON that we want it to infer some kind of type. And then on line 9, what we can do is just give it throw actual data at it and then what is put as the value in AW is actually a record type, is a value of the record SK, right? And then we have access to the attributes, right, as types. Any questions? Sorry, okay. And then so how are Idris type providers different? Well, we can compute types in Idris itself, right? And because of its dependent types. And so what we have here is an example piece of code where with the name of the type itself is CSV type. So that's the declaration on line number 1. Line number 2, we have this constructor, this value constructor, make CSV type. And we accept a delimiter character as an argument, a nat, which is a natural number, as a second argument, and a header, which is a vector of length n of strings. And then we can give back this CSV, this instance of CSV type. That's all this is saying. Does this make sense to everyone? Oops, sorry. So these funny things here, that's just saying that go to the next argument, so to speak, or the next thing, the next type in a function. So if you're familiar at all with just reading Haskell or Scala, in Scala this would be the equals greater than sign. So still awake? Okay. Yes, go ahead. Oh, okay, great. So Idris. Let's review the provider type, okay, in Idris, and this is what we have to return back inside of an I/O action to be able to create this type provider. And who here is familiar a little bit with either Haskell or Scala? Okay. Oh, great. Okay, fantastic. So basically, provider is like the either, except we only have one type argument, right? And we've fixed the second type argument of either to string. This is basically all it is, right? So this is an either where the error side is in fact string. That's it. Okay. So how do we start off? Well, we declare a module to put our provider action in. And then we add in some helper, some axioms, right? Some definitions, so the type, right? And then we have this function that we can infer the CSV type given the header string, just the header as a unparsed string. And then we can actually create the CSV type, right? So here I'm creating a CSV type provider for some CSV data. And then we have the type provider action definition. And so this is, I've called it CSV type. I probably should have named it something else. But the first argument is char, right? So this is the delimiter. The second argument is the string. And the final part is an IO action where inside we're returning a provider of CSV type. And this is basically the mechanics of the provider part, right? All we're doing here, since a lot of you are familiar with Haskell, this should read almost identically. So we would read into the lines, right, from a file that is given as the second argument. And then we do a pattern match on the lines that are returned. And if the lines from the file are an empty list, then we report some kind of error. And then if it has at least one element, we know it has at least one element because it's not an empty list, then we can provide the actual header, right, and from the infer CSV type. OK, so now we want to use this thing. So how do we go about that? OK, so this is just boilerplate. This is just the main stuff. We'll import the module that we just defined and this data named vect type, which is not automatically imported for us. And we've created some helper functions here, get birthday and get name. This is the same data, except in CSV format of the JSON that we saw on the fshop slide. So given a row of type T, which is the CSV type that we infer, then we produce a string, right, which is the value at the birthday column, right, given a row. This is all this is saying. And the same here with get name, except we're changing the name of the field. OK, so now this is, to use it, we just say we want to use the language extension type provider. And then this is really the magic. This is all there is to it, almost, right, is that we tell it, OK, we want the type provider using the CSV type function that we defined in the module to read in that file using this delimiter, the second argument, the comma. And we're going to name that type T. And so that T reference is now available to us through the rest of the file, right? And so this is what we might do with it. OK, this is not very interesting, I admit. All we're doing is we're reading in that file. And assuming that we get some rows back, we can just map over all of the rows with get birthday, right? Birth year, sorry. And then show all the birth years and do the same for the name and show all of the print line, all of the names. OK, not very inspiring yet. But as we can see, we can actually compute and calculate types from some kind of external source, right? So questions so far? OK, you're still awake, I admit. OK, a couple. So there's this other thing that I think is really powerful in combination with using a language like Idris, and that is the Curry-Howard correspondence. So informally, we've got propositional logic, right? It has a number of concepts. It has connectives, and it has quantifiers, and some other things that sound way too fancy for what they are. And they correspond to programming language features. And last year at Strangeloop, I believe Philip Wadler was presenting the keynote, or at least a talk on propositions as types. And if you haven't seen that, you really should. And consequently, the proofs in some languages, at least, that have total checking are basically the proofs, the definitions of those types are the proofs. OK, so let's have a look at a math. Anyone here afraid of maths? OK, Okay, a couple. Okay, this is only to show that there is a mapping. Okay, this is not some horrible, like, it won't be too horrible, I think. Okay, don't trust me at all, but, so a really simple proposition is that for all n in the naturals, right, n is either even or odd. And the definition, we've got some definitions, right? So even is defined as for some p in the naturals, we've got n equals to 2p. And, for odd, we've got the 2p plus 1, right? That's all this is saying. Now, the second line here in parentheses is like a total math encoding of this whole proposition, right? So this is the very English version on top, right? And this is just the mathy version. And that's kind of a little bit programming languagey, maybe. And so if we look at how we could define this in Idris, right, we've basically got this type. So for all n in the natural numbers, right, there exists a p belonging to the natural numbers such that it's either even n or odd n. And we're using types here as basically type constructors, basically to, what's the right word? To create a predicate, right, in this case, because we can't construct an even value unless it really is even. And I think I have an example at the end. So this is proof by induction, and this is the math induction. This is the math proof, right? So we'll get to what the Idris definition looks like. But first, let's just do a review, right? So we need to encode, or we need to translate the notion of truth to programming, right? And in, for example, Scala, we've got this unit type. And then in Idris, it's also called unit, except it's empty parens. And this is very similar to Haskell. Okay, so falsity, is something that should never be. And so it needs to be uninhabitable. And that's just a fancy word for saying that you can never construct a value of that, right, in your programming language. And this is sometimes called the bottom type. I just love saying the bottom type. In Scala is called null, this type that's available to you to express this kind of thing. And in Idris, it's called void. And so if you ever need to express in Idris that something should never be, right, then you can have it go to void at the end, right? And that is basically you expressing that this condition should never be met in my program. Okay. So implication. So when A implies B, we can say, given a value of A, we can return a value of B, right? That's all that means. And so this is just going from A to B as a function and defining that as a type. And that's how you would do it in Scala on the top, and in the first two lines are what you would do in Idris. And then line 4, 5, and 6 is the type signature and definition for a really simple idea, right? This is a proposition. It's not maybe very interesting yet, but we've, so given a Boolean or a bool value, we can return a nat. And in fact, this is total, and I forgot to put total in there. But we can actually show that this is consistent, right, in the logical definition, which just means that everything checks out. Everything that this function, this type depends on is just makes sense, right? There's no contradiction. And so given, there's only two values of bool, so if it's false, we return 0 in the nats, and if it's true, then we return 1. That's all that is. It's maybe not the most interesting proposition, but you're starting to see that all of these things really are propositions, but we can make more interesting propositions. I'm sure of it. So negation. Now, there's a special type in Idris for this, and this is just not. And then in Scala, we would just take an A. If an A should never be, if an A should never exist, we can just like have it imply like this falsity thing. And that's all that means, right? So this is logical not, and we use this every day in all of our if statements or whatever, right? Or whiles or something like that. So this is not foreign to any of us, I think. Conjunction, a really fancy word for and. We all use this, right? On the type level, this can just be expressed as a tuple, right? And in Scala, that's how it's written. And then in Idris, that's how it's written. It's just a pair. It's it takes two type arguments, right? And one thing, you can also express this anding as a record type or a product. So if you're familiar with that. And so disjunction is a really fancy name for or, exclusive or. And in Scala, I did say it was kind of related to either the standard library one, almost, right? If you're familiar with Scala Z, it's more like disjunction, the V one. And if you're familiar with cats, that's a lot closer to the XOR, XOR type. And then in both Haskell and Idris, this is either, right? And so, okay, so consistency, it's like in logic, you just want to make sure that all of the propositions, when you combine them together, actually make sense, right? Everything checks out. And this would, so when you say consistency, you want to make sure that they're total, like all of the functions that you care about or the types are total. And most languages don't actually really give us this ability, right? Not quite to the extent that some of these research languages have for a long time. And so we can express this in Idris with total, the keyword total, and we can even make it the default in our file, right? And just say, by default, just make everything total, unless I want to say it's partial, in which case, on line 13, you can see there, we can say this effectful main is going to be partial, because we can't really type check that if we say it's total and it's really not. Okay, so induction, always trying to say, so induction is a really, really important idea in mathematics and logic. You need to be able to prove things a lot, by this, right? And all we're doing here is translating this to recursion, right? And so a lot of languages support this. And this might be like maybe the scariest slide, so I apologize so far. So given, for all n, right, in the naturals, and for all m in the naturals, then, and this is actually a type, this particular term here. And it's, so the successor of n plus m is the same as equivalent to n plus the successor of m. This is all this is saying, right? I think this is pretty common sense to most people. We just take this for granted, but anyway, so we can actually prove this for, apologies. We can prove this with the base case. So z is just a symbol for 0. And then m is just the second argument here. And Idris can figure this out for us. And so we can just tell it raffle, right? And then on line 6, we've got, since it isn't 0 anymore, because this is just pattern matching, right? This is just a new clause of the function. And this is a successor of k, some k. We don't know what k is. And then we take the m, and then we can do recursion right here, right? Oh, sorry, I apologize. I renamed it to blah, and I didn't rename it in the definition. So this doesn't type check. Oh, I cannot be endorsed for type safe presentations, I guess. I apologize. So quantifiers, really, really fancy word for describe how many of something, right? And so universal quantifier, all that means is for all x in something. That's all it means, and it's not really that interesting, but this is an expression of that in Idris, right? And so we can label types in the type signature itself and then use them later on. And that's what that means. And then existential quantifier is just saying there exists something such that. And so you can read that here. So for all n in the naturals, there exists a p in the naturals such that it's either even or odd, right? So this is an approximation to a proof of the very first proposition that we had, right? And this is actually, it's important now that we see that all of the different things that we just talked about, the translations from logic to programming language features, are, might all be there. But it's really not that hard to read this. And of course, I kept a type hole because it wasn't going to fit on the slide, so I apologize. But in Idris, you can have these type holes and then fill things in later when you feel like it. But this does, in fact, type check the original one, I promise. Although you don't trust me anymore because... OK, so I know that was the most math that you're probably going to get today, maybe, hopefully, I don't know. So how would we encode more interesting propositions about infrastructure? Well, I think I have a bug in the English, so I apologize. So I'm going to read you the type out loud in English. So we're going to get an account and a region, and then an X. And because we've got this, we can define a type provider, right, that extracts the number of availability zones per region. We can get all this information and then pump it into this function, right? So this isn't a function that would use the type provider or call it, or it isn't the type provider action per se, but once we have that mechanism in place and we've defined the provider and we're in some kind of action that we can call the provider and extract that information, we can make more interesting propositions about our infrastructure. And so X here will symbolize the number of sorry, what was I thinking here? I need to write better names, huh? So region net. Yeah, so the number of availability zones, right, which we already know from when we build our type provider. And then we can say there exists an n belonging to the natural numbers such that, and here are some definitions that are outside of the scope of this particular slide, but a cluster of some multiple of x and m, so x multiplied by n, and then for some service, right? So all I'm saying here is that we're deploying a cluster that is a multiple of the number of availability zones, so we have like an equal distribution of everything. And that was what I intended to write above, and I didn't do, so I apologize for that. And so we can actually start expressing some of our infrastructure requirements as types, and then using the Idris interactive type checker to kind of give us hints on how we could go about like proving that with our definitions and our axioms. Okay, so what we've been able to do is infer rules from evolvable metadata. We can proactively take advantage of new account capabilities. So we'll be reading in, the availability zones from the AWS API at the time that we want to create our deployment plan. And we can, it's usable across accounts because we just have to use different account credentials, right, to be able to point at the API. And then we have this high-level language with what I'm going to call superior assurances. So we could have written a lot of this kind of interactive stuff with Ruby, but we don't have a number of things that Idris provides in terms of the assurances, we can't do total checking. We can't check that a function is total. We can't check that, that everything is going to be appropriately typed, right? And things like that. So Idris is something that can provide that for us, right? So questions? Yes.
Is this like a product that we can look at and see? More of like
Fantastic question. So there is, I haven't put any code up yet because I didn't want to put anything up, but there's, on GitHub, I just created a repository where I'm going to be putting up this kind of thing and walking people through not just this, but also the, how we can encode propositions as types and maybe creating various definitions that would be useful for AWS kind of stuff. So, so this will be there probably in the next couple of days. Go ahead.
In your example, you showed 4 quantifiers, but it wasn't clear why one became for all and another one became there exists.
Oh, okay. In here?
No, keep going back. Yeah, that one. No, not that one. The one that had the P. Yeah, that one.
Okay.
So with the left one, and for all and nats, there exists a P. How does that happen? The for all and that there exists, it doesn't show up.
Oh, okay. Great question. That's a fantastic question. So I think on this slide, I didn't do a very good job of this, but I believe that, so this is almost the same thing, just a slightly different such that, okay? And so given an n, so for all n, right, there exists a p belonging to the nats such that it's either even or odd, right? And so here we show proof, right? So we could have said REFL, I think, here. Idris would have been able to.
I'm talking about line 9. You keep saying for all and there exists, but there's no there exists or for all in there. Is that by convention or is that by order?
Oh, sorry. I understand the question. So this whole term here is called a dependent pair in Idris. It has special syntax. You can represent it as a D pair, so the D pair constructor to look a little bit more similar. And so then the first argument would be the P, like the labeled P colon nat, and then the second one would be the such that condition. So this is just a special syntax. And so the thing, if you've got something in brackets and it's got a double asterisk, then what's beforehand is the there exists such, and then after that is the such that condition.
And otherwise it's universally quantified.
Yeah, yes. Okay. Yes. Thank you for your question. That was great. Go ahead.
So do you envision this as something like where one of your early slides talk about, printing out what your AWS environment would be like without actually building it? Do you envision this kind of like, so like Terraform has that kind of thing where you can basically, envision it and apply it? Is that kind of what this is as well?
For sure, yes. Except that, yes, it is definitely similar to that. I definitely want to build out deployment plans and also deployment execution plans, right? So there's, for example, I want to get to a point where I can actually express in proposition or types and then implement something like I want 0 downtime deployments, right, for this particular service. And then it would be able to either generate a deployment plan that can do that, or it returns me something, an error, right? Yeah.
Using this, you should be able to just like print out your entire AWS within without actually doing anything.
Correct. Yes. Yeah. Go ahead.
I was curious about this proposition on line 9 again. Obviously, the n is universally quantified and is on the other side of the implication as well, but the p doesn't appear in the thing where it exists.
Yes. Yes. So here, maybe this might help a little bit. This is a realization of that type, So this all just boils down to, this is a value of this type. So this just becomes a type. And this is just special syntax.
Oh, so it's actually more like a pair.
Yes, they're called dependent pairs, yes. So this last, the result part, is called a D pair in Idris. And this particular style is totally just syntactic sugar for that D pair.
Okay.
Yeah. And so we're providing for the base case here the evidence. And we're just saying 0, there exists a 0 such that we can return left even 0, right? We're just providing that evidence for the base case as a value of that type. So go ahead.
What sort of facility do you have for controlling the error messages that happen if you have a type error?
Yes, so there is an error handling portion in Idris which allows you to actually plug in like different error messages depending on your domain-specific language. I pulled that out actually because I didn't think I had time. That's a great question. So we would be able to say much more concretely or more usably to the user, hey, we don't have the requirement for you to deploy a production cluster says that you need 3 availability zones, but this region only has 2 available to you, so we can't do anything. Yeah. Any other questions? Go ahead.
Is the double asterisk both for the syntax of the dependent type and its constructor? Because I saw in the 911 is still double asterisk there.
Sorry, can you repeat that?
Is that what is the syntax for the constructor of the dependent pair? Because I saw in the type level and in the value level, they use the same symbol there.
Yes. So actually, let me go back a little bit. Nope. So here, okay, so this is a regular pair. This is just a tuple, but there's also a D pair, and it will take one value of type something, like so it takes it's 2 type parameters, right? A D pair, right? So you've got the type of there exists some value in that, right? And then you've got the type which is representing the predicate or the particular proposition that you want to hold. So what might be confusing is that in Idris, predicates are basically some value to type, not some value to bool. Bools should probably never be in your Idris programs. So thank you for your question. I think one more? Oh, no more, sorry.